So welcome back again to this lecture in the series of lectures for magnetism and matter. Okay, and today we'll talk about magnetism and the Gauss law when applied to magnetic dipoles. Okay, and this goes like this. I read it. The magnetic field dot ds, which is the surface vector, over a closed surface. CS stands for closed surface. This is equal to 0. Okay. This is the Gauss law for magnetism. But this Gauss law for magnetism is distinct from the Gauss law for electrostatics, which we learned as for a closed surface, E dot ds is equal to the total charge enclosed by it divided by epsilon naught. Okay. Now, in this Gauss law, if we take a Gaussian surface, this surface is called a Gaussian surface, then the number of magnetic lines of field entering is equal to the number of lines of field leaving the Gaussian surface. So the net flux phi is equal to 0. Or we can write that B dot ds over the closed surface is equal to 0. Of course, even if B is not equal to 0 and S is not equal to 0. Surface is there, the magnetic field is there, and wherever there is a magnetic field, I told you that there will be an energy density, okay, which is half epsilon naught E square in the case of electrostatic fields, and half instead of epsilon naught we'll write 1 upon mu naught, so into B square. So B square upon 2 mu naught, that will be the magnetic energy per unit volume wherever there is a magnetic field present. Okay. So I can write that phi B flux is equal to this thing at B dot ds, B dot ds is equal to 0. Okay, or a closed surface. What it means, what it implies, it is not equal to 0 but instead is q upon epsilon naught, because in this case there is a charge enclosed. That could be positive, that could be negative, but a surface, a closed surface can contain a distinct charge, okay, a positive charge and a negative charge. But since there are no monopoles in the case of magnetism, poles occur in pairs, north-south pair. Okay. Therefore, okay, the net magnetic flux through any closed surface is 0. So this is about the Gauss law. Okay. Now I must tell you something. That there used to be a time, and I also used to be taught like this. This is the old school of thought, where we considered the bar magnet, or for that matter any coil etc., to consist of two magnetic charges, north pole plus qm and south pole minus qm, and the separation between the two of them was taken as 2L. And then you used to calculate the magnetic field on the axis, on the equatorial axis, here, there, everywhere, anywhere, and the end result used to be the same. Okay, but this had to be abundant, but historically this was there. Therefore, a mention should be made, and we will not condemn the people who are using this kind of an approach, because it was a very effective kind of an approach. And even today, when you are trying to solve multiple choice questions, you can make use of this, because nobody is going to look as to how you have arrived at your answer. Okay, even some people are claiming that you come to us, we'll give you 50,000 questions and you will be able to crack the JEEE or other examinations. I don't subscribe to that, because what cracks the examinations, particularly in the case of the IIT system or IIIT system, is this. You have to use this. Okay. And you have plenty of it, so you can use it, of course. Now, let's go beyond that. The next topic as Earth's magnetism, which, if measured all over the Earth is mapped, then this magnetic field due to Earth is found to be numerically 10 to the power of minus 5 or around Tesla. Okay. Of course, the directions, etc., are different at different longitudes and latitudes. What are the longitudes and latitudes? The geographers worked very hard, okay, so that they could draw lines which were called longitudinal and then latitudinal lines, north hemisphere and south hemisphere and etc., etc. Okay. So they found that there is a North Pole, geographic North Pole, and there is a South Pole, geographic South Pole, etc. And the location also we know as has been given by the geographers. Okay. Like we say about physics and we say about mathematics, the one line with which geography is started, it is said that geography is the mother of all sciences. Okay. Physics is the mother of all sciences, mathematics is the mother of all sciences, etc., etc. I don't know how many mothers the sciences have. Okay. I don't care also. Now, when the magnetic field is there, and this we can measure with the help of compass needle, okay, which is a permanent kind of a magnet, which is either pivoted so that it can move in a horizontal direction, okay, around a pivot like this, and sometimes it is pivoted like this so that the needle can move up and down. Okay. Now, this is for sure that there is magnetic field. Earth's magnetic field, a horizontal component, a vertical component, and this and that and that and this. Okay. But even today we are not sure what causes the magnetic field of the Earth. So there are many theories that were proposed with guesswork, okay, and initially people thought that there is a giant, big bar magnet through the center of the Earth, going from the South Pole to the North Pole. No, it could stay in the body of the Earth, and it is because of that the magnetic lines of field, okay, they emerge and go and this and that and that and this, like that. Another thing was that later on people thought that there is a convection current. Convection current means the mitre moves with the current. Convection, if you take it, okay, I told you about three things, the conduction, the convection and the radiation. So this is the convection current of molten iron and nickel in outer core of the Earth. Okay, just because the temperature at that point is so much so that iron and nickel can be in the molten form. Okay. But tell me, is it iron atom and is it nickel atom? then the answer is no. If they move, then we will not get a current, electric current. So they have to be charges, and these charges have to be the positive ions of iron and nickel will move in the outer core, and the currents have been calculated, the magnetic fields have been fixed, this, that, etc., etc. There is also a theory that in the upper atmosphere there are currents, and because of those currents the earth exhibits, shows, okay, a magnetic field all over mapped out. So there is, that gives rise to whatever. There is a magnetic north pole and there is a magnetic south pole, which is situated at the actual location, which is close to the geographical north pole and the geographical south pole respectively. Okay, we'll talk about that. So, taking the earth as a magnet, we'll talk about the declination d, which is the angle between the magnetic and the geographical meridian. Okay, so just roughly, I have made the earth, a section of the earth, and then we have taken the geographic meridian, which goes in the red lines, and because the magnetic north pole has an inclination with the geographical north pole going to the center, and this is about 11.3 degrees as per the record given in the books, latest records, and this may change also, okay, in due course of time. Maybe in the days of your great grandson it may become more. Okay, so this is the magnetic equator. This line has been shown as the magnetic equator, and this line has been shown as the geographic. One thing very interesting is that the magnetic lines of field, they enter into the north pole over here and they get out of the south pole. So this is one thing which has always to be borne in mind, because the things developed historically that way. Okay. Now what is a meridian? A meridian, for example, I'm in Aligarh right now, okay, then if Aligarh is situated here in the north hemisphere, okay, then if I have a line which passes through the north pole and the south pole and the point under consideration on the round surface of the earth, then we can take these points and then cut through it, just like we cut a melon or a watermelon through its center. So that plane is called the meridian. So meridian is a vertical plane passing through the point and the corresponding poles. Okay, so there will be two meridians. One is the geographic meridian and the other is the magnetic meridian, which has been shown over here. Okay. So true north, true south, these are the geographic ones, and this is the needle is going to indicate in the direction of the north pole, magnetic north pole, and this in the direction of the south pole. There is an angle between the two of them, and this angle is called the angle of declination and simply declination. Okay. Magnetic needle in the horizontal plane, that is, if the pivot is like this and the magnetic needle is staying like this, okay, then this indicates this side it is north and this side is south, and this is how the needle will give the direction of the north and the south poles, the magnetic north and south poles, which are close to the geographic north and south poles respectively. Now this D is higher at higher latitudes, Latitude is the lines that we draw here, okay? And longitudes are the lines that we draw here, from here to here, from here to here, here to here, etc. And these are at different places. Any place you look at in the atlas, and the atlas will always give you the location of the place in the terms of the longitude and the latitude. Okay, you can look for yourself, and you know it from your previous studies in geography. Now, declination is higher the higher latitudes. Delhi and Bombay, they are close to the equator in the northern hemisphere of the earth, and it is found, and this is given in the books, I don't know, that the declination in Delhi is 0.41. Of course, Delhi is a spread up thing, so maybe East Delhi and West Delhi, and they may have different values, but this is a value approximately given for Delhi. There is no New Delhi, okay, and in Mumbai this is 0 degree 58 minutes. This is the sign of minutes, okay. So you cannot find a value which is 0 degree 67 minutes, no, because 60 minutes is equal to 1 degree, okay. And if you are going to be more accurate, then there are seconds also, and the seconds, if they are 17 seconds for example, I will write like this, okay. The second thing is, right, the second thing is called inclination, also called the angle of dip. But in this case, we have to have the pivot like this, okay, and this is the needle. This is the needle, and what will happen in that case, the needle can move in the vertical direction. So what happens is that the needle may dip like this or like this, okay. So that angle of dip is different in the northern hemisphere and southern hemisphere respectively, and we'll talk more about it in more details just now. For the angle of inclination or the angle of dip, the compass moves in a vertical plane, okay. So which has been schematically shown over here, that this is the magnetic north pole, and this is the point P under consideration, and we find that the magnetic field due to the earth is in this direction, BE, and the horizontal component, of course, it is tangential, then this is equal to HE, is in this direction, and the vertical component is in this direction, okay. This angle is the angle I, which I have just blown up a little over here, okay, where this is the B, and this is HE, and this is ZE, the Earth's magnetic field, the horizontal component and the vertical component, and this is the angle I which has been taken over here, right. Just to give you an idea, a glimpse of what is happening, we take the magnetic field which is like this. This is a what do we call it anyway, I don't remember exactly, but off the cuff, what is it? This is HE, and this is BE, and this one is ZE. This angle is the angle of declination, and this angle is the angle of inclination, okay. So look here, this is what I have shown here in the form of a right angle triangle. This is our angle of dip I, and it could also be angle of dip like this. So there is a green triangle and there is a blue one. It could be like this or it could be like this, okay. So I have BE over here, ZE is the vertical component, this is the horizontal component. Here it is B, this is the horizontal component, and this is the vertical component. Okay. Now, let me tell you one thing, share one information. In most of the northern hemisphere, okay, north pole of the dip needle normally tilts downwards. Okay. In the southern hemisphere, it tilts upwards. That is the south pole of the dip needle tilts downward. Okay. HE I can write as equal to B into cos of phi. Right here you can see. And ZE is equal to B into sine of phi. Right? From the easily drawn right angle triangle. So tan of phi is equal to ZE upon HE. Or you can say that it's the arc tan or tan inverse of ZE upon HE. So if those values are known to us, we can find out the value of I, etc. To wind it up, I am taking exercise in which in the magnetic meridian of a point under consideration, place, HE is given as 0.26 Gauss. Okay, 1 Gauss is equal to 10 to the power of minus 4 Tesla. The angle of the dip is given as 60 degrees. Okay, cos of 60 degrees we always know is equal to 1 by 2. So they are asking what is the value of the Earth's magnetic field. So first of all, we should, okay, draw the right angle triangle. This is B and this is HE, and of course I can write it as the vertical component ZE. In case they ask about Z, then we can. Anyway, so HE upon B is equal to cos of 60 degrees. From here we can see readily is equal to 1 by 2, and this gives therefore BE, okay, is equal to 2 multiplied by HE. So when I multiply it, readily I get this value as 0.52. They could also ask you what is the value of ZE. They could give us the value of ZE and ask the value of BE or HE, and the angle is known to us. So that way many questions can be generated and solved readily with the help of this triangle. So it has been good to discuss the Earth's magnetic field and other aspects associated with this thing. Okay, and now next we move on to magnetization and magnetic intensity. Magnetization is of a material, a magnetic material. Okay, and it's interesting and it equips us to deal the things further. So I hope that you revise this when you come back for the next lecture. Thank you very much. See you.